Welcome to the GSOC Geology Hour, our monthly gathering of geology enthusiasts brought to you by the Geological Society of the Oregon Country with support from the Beverly Vogt Scholarship Fund and the Portland State Department of Geology.
Alyssa, do you want to introduce your classmate?
I absolutely can. Yeah. So, Angela Stetson is a second year master's student at Portland State. We're both in the same lab group. And yeah, I think after that, I'm going to let you introduce yourself, Angela, and maybe mention a little bit about what you do for research and how kind of you were inspired to bring up this bit today.
Thank you, Alyssa. Let me get my screen share started while I tell you a little bit about myself. I am, like Alyssa said, a Portland State graduate, and I am studying under Martin Streck, and I'm studying unassigned basalt from Eastern Oregon. I like to call them the orphan basalts. And so I'm classifying these unassigned basalts as one of the major basalt units in Oregon, either the picture gorge basalts of Columbia River basalts, or maybe Steen's basalt, or maybe Strawberry volcanics. So I will be completing this around June time. I hope to defend. And in the meantime, I'm also making a map of Craft Point Quadrangle. And right now I'm deep into writing the report. So today I am talking to you about the Laki fissure eruption of 1783 to 1784. This was a presentation I had originally given like a little bit less than 3 years ago for my very first presentation as a college student for volcanology. So to start off with, Iceland is the focal point of the North Atlantic Igneous Province, or the NAIP. The NAIP is a spreading ridge and also has hotspot volcanism. Within Iceland, there are 5 major volcanic tectonic zones. We've got the northern volcanic zone, and then we have the Snæfellsnes volcanic zone, and then there is the western volcanic zone, the eastern volcanic zone, and then there's also the Órefellsjökull volcanic zone, which is not in any of these maps. And as I continue, I'm going to try to say these Icelandic terms as accurate as I can, but I will probably butcher it and probably go a little bit slower than I would normally talk. So Laki, also known as the Skaftraldar or Laki Giger, is found within the Eastern Volcanic Zone, and it is a member of the Grímsvötn volcanic system, which is Iceland's most active volcanic system, with one eruption every 2 to 7 years. So Iceland sits upon the mid-Atlantic ridge. It is within a divergent tectonic zone where the North American plate is spreading from the Eurasian plate at a rate of 2 centimeters per year, with both plates taking up a centimeter each. Rifting is caused by this divergent tectonism, and it causes grabens. Magma prefers these grabens because they provide a path of least resistance. In the Laki region, which is over here by the Órefellsjökull belt, it has some of these graben faults. So in this map here, we have a bunch of orange polygons, orange-colored polygons that basically are mostly tholeiitic basalts. But also within the central region of Iceland, there are intermediate or andesitic to silicic or rhyolite volcanism.
So I want to take a second and interrupt if I might. I wanted to ask, just in case people are unfamiliar, what is a graben and what is tholeiitic basalt?
So a graben is a block of earth that falls down in between faults, or in between spreading crust. And so there's a fault on one side and a fault on the other side, and as it spreads apart, that graben falls down. And then
Awesome.
You said, what is basalt?
Tholeiitic basalt. What's the significance?
Tholeiitic basalt. Tholeiitic basalt is commonly found at mid-ocean ridge basalts, and it is basically more or less evolved basalt that comes from deeper within the mantle, generally speaking. Does that work?
I think so. Yeah.
Okay.
Another distinction could be that it's just a more uh magnesium rich iron poor variety. That
Yes.
but now I'm convinced that I've mixed that up. So
No, you're right. I
just a
just try
flavor.
to simplify it, it is a flavor,
Sure.
yeah.
A flavor.
Okay, so continuing on, I guess. I have here a very old map of the region around surrounding Laki. It was produced in 1771, which is before the Laki eruptions. So to get you acquainted with the region, to the northeast off the page, we have the Grimsvötn volcano, which is under the Vatnajökull ice cap. And then we have the Western Skaftafellsfjall, or the Fire District is which I'm going to call it because it's easier. That's what they call it too. And that's in this region here. And so within this region, there are two main rivers that meet the Atlantic Ocean. We've got the Skafta River, which is glacially fed, and it also has Highland Springs. It flows west and then south through the gorge, and then east again once it emerges from the gorge, and then southeast to the ocean. Its highest discharge is during the summer, and its average discharge is 115 cubic meters per second, and it drains about 3,600 cubic or square kilometers. Then we have the Verfisfjord, I can't even say that one, glacially fed river, which comes down this way, and it flows south to southeast. Its summer discharge is between 5 to 150 cubic meters per second. There's the Galti Röskuldar Ridge, which is 40 to 50 meters high, and it's an oceanic platform. This encloses the Varmundalar Valley. Within the lowlands, we've got many small farms, and then the Kirkjubekjarlastur rests at a major bend of the Skafta River. Beneath this is the Icelandic hotspot, which is one of the reasons why responsible for Laki and the previous Elgja fissure system. And then finally, there is Mount Laki, which is a pre-existing volcano. It's right around here, which is where most of this lava came from. So jumping into the actual eruption and what led to it, Grimsvötn started to erupt between May 1783 and May 1785. This triggered the Laki fissure system. This fissure system is southwest trending and erupts from it, which is a characteristic of Grimsvötn volcanism. In May, somewhere around May 1783, the Skafta River produced a foul odor that the residents of the lowland regions could smell. This indicated that gases were escaping through cracks near the river and which signaled an eruption. And then mid-May to June of 1783, seismic activity was increasing both in duration and frequency, and probably strength as well, intensity. And this indicates the formation of dikes. And then in May of 1783, fires were reported in the highlands from residents, and this indicated possibly an earlier undocumented eruption that is not part of the actual eruption of Laki. The Laki eruptions is split up in two different parts, phase 1 and phase 2. So starting in June 8th, there was increased seismicity, which led to explosions, which led to what was called columns of fire. And atmospheric and volcanic rain was mixing with black ash and Pele's hair, and this occurred for several days. And then fire fountains were the only thing that were seen for the first few days. They didn't know anything about lava or anything. And then on 11th of June, the Skafta River evaporated and steam was rising from the gorge. Lava was observed following that steam, and then that lava overfilled the gorge and surged out onto the farmlands. Following this, a series of 6 more fissures opened up like a zipper. There were 5 subplinian eruptions, which means they had 11 to 13 kilometer high explosion plumes. And then there were also 2 phreatomagmatic eruptions, which is where lava meets water and it flashes to steam. During this time, there were also 3 Grimsvötn volcano eruptions, and this added to the tephra fall. And residents constantly reported a bad or acrid smell from the ashfall and waterways. So from these 6 eruptions, there were first 2 Laki eruptions between the 14th and 24th of June. They distributed tephra to the north and southeast, and then there was 1 Grimsvötn eruption that distributed tephra to the southwest. The rivers evaporated with steam and lava extends into the lowlands. And then between June 25th and July 12th, 2 more explosions occurred. Tephra was reported to the west of the eruption as well as to the southeast. Again, the rivers evaporated to steam and lava spread through the lowlands. And then continuing on, we've got July 9th through the 21st, there were 2 more eruptions. And this tephra deposited to the northwest and the southeast, as well as 2 Grimsvötn eruptions, which deposited generally to the southwest. Again, the rivers evaporated to steam and lavas distributed closer to this village this time, over here in this region. Okay, then we get into the precursor and the main event of phase 2. Starting July 29th, they could hear boiling sounds in the distance, and a subplinian eruption of about 9 kilometers high produced pumice-like scoria that covered the southeastern portion of the region. And then on August 3rd, that boiling sounds led to steam that flowed down downstream of the Skafka. I think it was the Hervesfra gorge, but flowed as if it were like a river running down, but it wasn't water, it was steam. This continued for until the 23rd of August. But in July 30th through August 7th, crackling and rumbling sounds were heard the entire time. And then officially during phase 2 is started August 7th, and lava was observed at Mount Laki, which is right here. And the lava surged from the gorge to 1 kilometer beyond the highlands. And by August 9th, the lava had reached the lowlands from the gorge. For August 14th through September 14th, there was a steady flow of water flow of lava that began to wane. And then on the 14th of September, the first part of phase 2 ended, and a series of rumbles, ashfalls, lava surges followed like phase 2, followed like it did in phase 1. And then there was this temporary pause, just a very short pause, and the water was allowed to flow down the gorges again, not steam. And then we get into probably the final main phase of phase 2, which was between the September 26th and 29th of October. The pause ended and strong earthquakes immediately picked back up, and then lava flow followed. The lava impounded and dried the rivers up again, and then they assume possibly that this was actually a second fissure had opened up because lava was going through both rivers. And then the 25th of October, the last fire column was observed, and it was accompanied by a sandy ashfall. This lava the lava continued to surge, but then it slowed to a stop. And that brings us to the end of our phase. The activity diminished, seismicity. Oh, I'm getting ahead of myself. Sorry about that. The activity diminished for a little bit, and then again, seismicity increased. Foul smell came from the northeast, signaling the final main event. Then the final main event, lava flowed, but slowed down to an end on January 7th. But Grimsvötn continued to erupt for another year and a half, something like that, between the late January to 26th of May of 1785, which also deposited tephra and ash in the region. Okay, so following the main phase events, fires were seen until the 14th of January. And then the sulfuric smell, that the acrid and bad smell, was smelt until throughout the entire year of 1784. The seismic swarms followed a nasty freeze for some reason. And then but the residents said that they were different than the ones that occurred prior to eruptions. Contamination of the water had cleared out by spring of 1784, but the continued eruptions at Grimsvötn deposited at least 2 more events in the fire district. The various gases from the Laki and Grimsvötn volcanoes, mostly sulfur and fluorine, contaminated the surrounding pastures and water sources, which killed livestock, plants, and humans. The eruption also caused a change in the climate that sent Iceland into a period of famine. So talking about the gases, this is one of the things I really wanted to focus on. I had all kinds of other stuff I was going to talk about, but it's like, yeah, this is most important. Sulfuric, or SO2, was jetted into the air at 9 to 12 kilometers. This reacted with the water in the atmosphere and then was converted into sulfuric acid. This was transported along the European jet stream, which sent smog through the mainland of Europe. A total of 122 megatons were degassed over that 8-month period, and that smog encompassed most of Europe, down to the Mediterranean Sea, and even to the Ottoman Empire. Some reports also suggest that it reached the southern ends of Tunisia. People reported sore eyes, and those that had underlying medical conditions had adverse reactions. Also, the plants were affected by what was called honeydew wilting from overnight condensation of the sulfuric acid, which destroyed crops. Then there was also 304 megatons of CO2, and this peaked as high as 600 megatons. So fluorine from decast hydrofluoric acid caused fluorosis, which also killed livestock in Iceland. As much as 11.5 thousand cattle, 28,000 horses, and 190,000 sheep were killed from fluorosis. Both sulfuric SO2 and CO2 contributed to a marked incline in mortality rate of Iceland and Europe from the starvation, dehydration, and poisoning. And the summer of 1783 was unusually warm, and the winters of 1783 and 84 was unusually cold. This also contributed to a possible decline or incline in mortality rate, and is attributed to the Laki eruption. So into the future, and this is why I wanted to bring this up today, because this is the future and we're experiencing it now. When Laki began erupting, we didn't know much about volcanology, but Reverend Steingrimson and others in the region had took detailed notes that allowed researchers to understand volcanology more than ever before. It kind of paved the way for volcano research. Laki is expected to erupt again, or another fissure within that same region. And Laki also poses a great model to assess hazards with gases and particulates, the dynamics of flood basalts, and characteristics of volcanic igneous provinces. I like to think of Silesia because, well, it's in our backyard, or literally it's in our backyard, and what we see from Silesia could actually help us understand what's going to happen with in Iceland, and also what we see currently in Iceland can help us understand better what happened to Silesia 42 million years ago. So, and more prominent to today is this Laki eruption could actually shed some light on the new Reykjanes fissure system near Grindavik. And that actually concludes that portion of this presentation.
Awesome job,
Thank you.
Angela. So
Thank
we
you.
had a few questions in the chat. I think are some really good ones. And I want to start with, I think you partly addressed this, but about the detailed descriptions that were taken at the time. How was it? It was, you mentioned a reverend
Reverend
someone.
Stein Grimson.
And
Grimson.
so were these just notes that, like, I don't know this person's background, they just basically recorded on what was happening at the time. Is that correct?
Yeah, so Reverend Stein Grimson is really the main contributor to what we know, because he was the pastor of that local village. I can't remember what it's called. It's that crazy long name, but he was the pastor of that region. And actually, a story that occurred is, well, while they were in church, lava was encroaching upon their church, and they prayed really hard and stopped the lava from destroying their church. But that kind of prompted the reverend to research this volcano a little bit more. So he made multiple trips up into the highlands to actually observe what was happening. And also there were, fishermen and hunters along the gorges that were actually the witnesses of the flowing steam rivers and the fires that could only be seen from the gorges and things like that.
That's incredible. And I think something I wrote down as a highlight is the power of observation isn't necessarily just held by who would call themselves scientists. I mean, I think people are scientists by nature. We ask questions. And just, it's amazing to me that, somebody just noting it smells really bad outside,
Yeah,
or, those are things that actually we can use in like current science
that's right.
to like be able to quantify things that otherwise would just be a mystery.
That's right. Yeah.
Which
And,
is
we're
incredible.
all citizen scientists contribute a significant amount to what we know as official scientists. So, you can't discredit any of it.
What differentiates a tephra fall from an ash fall?
Well, basically the size of particulates. I mean, they're used interchangeably a lot, but tephra specifically refers to gosh, I think it's centimeter or larger particulates that fall. And maybe Alyssa can clarify that for me, because I
Yeah, I
don't
can
deal
tap
with it a
in.
lot.
I actually don't either. I mostly deal with flows, but it's
Yeah,
come up.
right.
So essentially ash is tephra, but tephra is not necessarily ash.
There you
So
go.
tephra would be fall deposits in general, but could encompass larger particulate. Ash is very specific, which is less than, I think it's like, it's some fraction that makes sense, but I think it's a logarithmic scale. So it's something like 1/256th of an, I was gonna say an inch, but even then it's a scale with a specific size, but very, very small.
Right. Yeah, something like that.
Yeah.
And then one other question that came in is, how is the Laki eruption like Silesia? Both hotspot igneous provinces?
So one running theory with Silesia is that Silesia formed on a spreading ridge, and it was also part of a hot spot, or emerged from a hot spot. So really what Iceland itself is a modern day version of Silesia.
All right, thank you. Wonderful presentation. What I really enjoyed was you're starting with the geology, but bringing in the social and economic and health aspects of that type of eruption, and then linking it to Grindavik and what's going on there. Because I think people, I'm dating myself here, but in 1980 in Cle Elum, Washington, during that ash fall, I was smelling sulfur big time. And that's something that I think people don't, unless they've actually been in the middle of an eruption, don't really understand the gravity of the situation. And
Right.
it was an eye opener, let me tell you.
I think that something really big underlining this is if people don't understand like what this looks like for them, what would an eruption look like for them, it can just feel so disconnected. Like, why would you care if you don't have any point of reference? Like knowing, okay, this is how it could look is just one more thing to not only help people understand, but to bring them to being interested. Because
Yeah.
if we just stood up there and talked about different types of basalts and how they're chemically differentiated, our audience is going to shrink.
Right, exactly.
I'm going to be very excited about that, but it might just be a few of us in the room, and understandably so. But bringing in the context of like how that looked, like visually, like emotionally, how that affected people at the time, also it's just another way of connection, which I think is really important.
Right. Yeah. I mean, for my thesis, I study basalts. So, like even to this day, I'm like Columbia River basalt. But at the same time, it's like I myself am disconnected because I did not experience it. But once you start to realize the differences of what a large igneous province does, and how it has affected people during times of eruption, you start to think about things a little bit more in a detailed manner, I think. So,
I think that's true. Well, I think it's time to go on to our main speaker. And I have to admit, I don't have your background history, Dr. Guerrero, but I think it's wonderful that you're here today, and we're really looking forward to learning about the Wallula Fault. So if you could introduce yourself as you're setting up your screen share, that would be absolutely wonderful. How long have you been at DOGAMI, by the way? That's my question.
Thanks, Carrie, for the introduction. Let me go ahead and share my screen. Good morning, everybody. My name is Eduardo Francisco Guerrero. Everybody calls me Lalo. So you can either call me Lalo, call me Lalo, EF, or Eduardo, whichever one you'd prefer. Lalo seems to be my preferred. It is my preferred name to go by here in the States. So I am a geology hazard specialist with Oregon Department of Geology and Mineral Industries, and I'm here to share a brief, share a talk and kind of share a little bit about myself and share a little bit about what I'm working on with DOGAMI, and kind of share an update of what's going on with the agency, because there's a lot of changes that have been happening over the last 4 years, and excited to be participating and getting to share. So I guess go ahead and get started. Let's see if I can, let's see, where's my little laser pointer? Is that it? Yeah. See, that should, oh, that's the pen. Laser pointer. Okay. All right. So gonna start out with a little bit of an introduction and a little bit of sharing a little bit about myself, because While I have been in Portland for 7 years now, and 6 years, and have been in Oregon since 2010. I've participated with a few events, a few GSOC events with Paul, but just haven't had a chance to interact so much with everybody. So excited to just do an introduction to GSOC, then share a little bit about what are some publications that have come out recently and products that DOGAMI has been publishing over the last few years in the various areas of seismic hazards. Then I'll talking about some other co-seismic hazard products, and then some ongoing work that I and other colleagues are working on, and then sharing a little bit about what the road ahead looks like at DOGAMI. So that's kind of the general overview for the talk. So like to, I guess, wanted to start out today by sharing kind of a little bit of my own geologic timeline, so to speak. Back here, over here on the left-hand side, that's going to be the 2001 was when I moved to the United States and start my undergraduate education. And then I've spent the last 20 odd years working in various aspects of geosciences, but it was one of those subjects that I was lucky enough to discover as an undergrad, and just totally when I walked out of my first class, I knew that that's what I wanted to do. And I'm lucky enough to have had that chance to discover it, and lucky enough to dedicate a good portion of my career to education and also to research. So kind of here started out back in 2004. I, as an undergrad at Denison University, we're on a field trip to the Great Smoky Mountains. So haven't been back for a while, but it was a great introduction to Midwest and Appalachian geology on that side. So getting to see some of the old rocks that it sounds like some folks are getting to see on a regular basis who are on this call today. So that's 2004. Back then, had a mohawk and a few more piercings. Fast forward to 2003, and I joined DOGAMI at the end of 2022 in December, and this is at Brett's Club with colleagues from DOGAMI. So some of you might recognize Sarah Lewis and Ian Maiden, Lowell Anthony and Christina Applegate, who are all up in Washington for Brett's Club and learning about and getting to visit Missoula flood sites up there. So my current role in DOGAMI is as geology hazard specialist, and the areas that I'm working on are mostly related to active tectonics and earthquake geology. So a little bit of how I reached how I followed my geologic timeline. So I was born to a bicultural and bilingual and binational family. My mom is from California. My dad is from Mexico City. I was born in Ciudad de Mexico, and then I grew up in the city of Cuauhnahuac, which is now known, or it has been known as Cuernavaca, because Spaniards couldn't pronounce Cuauhnahuac. And that's the original name. And like this city is now it's technically a suburb of Mexico City, but it's outside of the transvolcanic Mexican belt. It's outside of the basin that contains Mexico City. A pretty wonderful place to get to grow up. Great views and great things to. So this is a view from my mom's house. And that's Popocatépetl, which has been pretty active fairly recently, and has been distributing ash in all directions around it. But growing up during the mid-90s in middle school, remember learning and watching the volcano start its activity again. And I'd come home from school, climb up on the roof, and just kind of sit there with binoculars and see if I could see the volcano erupting. But I didn't know that you could study geology, and I didn't know that you could that people could dedicate their careers to doing that. So it was just an interest that I had. growing up and doing my schooling. So during the school year, I'd be in Cuernavaca, Cuauhnahuac, and then during the summertime, my mom would come up to Northern California, where she would work at City of Oakland Feather River Camp, which is in Plumas County, and it's actually turning 100 years. It's a family camp that turns 100 years old this year, and she spent a lot of time. It's in a part of the Sierra called the La Sierra, because it's on the northern edge, right as you're transitioning into the Cascades. This is that's called the American Valley, and that's the crest of the Sierra. It's a little bit more subdued, less dramatic than the Southern Sierra, but it was still a wonderful place to get to spend time outside. This is where I got to see my first geologic map. And got to see all kinds of sedimentary rocks and granitic rocks, and was really excited about them, and started getting excited about them. So these experiences basically primed me to be a geologist, and that's what I didn't know that, like I said, I didn't know that that's what I could be until I started my undergrad. As an undergrad, I was initially interested in history and political science. And after taking my first geology class, I realized that geology was like history, but without people, and it stretched back much greater timescales, and presented that started my career, or my journey in this field. I graduated from Denison in 2005. I spent time in California. I spent some time away from Denison. I spent a semester in Grand Canyon at Northern Arizona University as part of the Grand Canyon semester. In 2003, got to take a rafting trip on the Colorado River for 10 days, and it was an incredible experience, transformational. Introduced me to a lot of outdoor recreation, a lot more outdoor recreation opportunities and jobs. So that after I finished my undergrad, after I finished my degree, I made my way to California and was working as a raft guide in California. And that led to a few years where I was wasn't doing geology work until it was time. I decided it was time I was ready to go pursue my graduate education, as motivated to continue learning and wanting to teach and wanting to do research. So in the detour that I took after my undergrad, I met my wife, Amarina, in California. She's from Oregon, and we knew that we wanted to be together, and I knew that I wanted to go to grad school. So when we're deciding where to go to graduate school, the stars lined up for us, because Andrew Meggs, that's Andrew over here, he was he was the advisor, my first choice of advisor that I wanted to work with, because of his research interests, and I knew that my focus was going to be involving tectonic geomorphology, because I realized that was where I was interested in. And we moved up to Corvallis in 2010 and started working with Andrew, and with Andrew developed a project from scratch. We built it up, looking at the surface expression of the Yellowstone hotspot in the Bighorn Basin, which is just east of the current Yellowstone caldera. So did graduate education, did my PhD, and at the same time that I was conducting my research, I was also involved with faculty researchers at OSU as part of an NSF grant called Increasing Diversity in Earth Sciences, which supported mainly community college students and undergrad students in research experiences with faculty at Portland State, at Oregon State, and at Cascade Volcano Observatory. and it was an incredibly fulfilling project to get to be involved in. I led field trips and coordinated workshops, GIS workshops, and doing professional development and kind of working throughout the academic year to help students prepare. But that basically, I left my PhD program after completing my degree, and my focus and my expertise is in tectonic geomorphology and quaternary stratigraphy. So looking at deposits, mainly unconsolidated deposits that are less than 2.6 million years old, and using and interpreting the sedimentary structures, distribution, and identifying older deposits and doing geochronology to interpret tectonic processes or active tectonic processes. And that involves aspects of structural geology and active tectonics as well. So that's a little bit of my preparation. And that's kind of what brought me to DOGAMI. So now kind of the rest of the talk going to focus on more of what's going on with DOGAMI right now. So just a reminder about the Oregon Department of Geology and Mineral Industries. I always like to have what our mission is so that we can communicate that and communicate that to the public. And it's always something that I know I'm not the only one within the agency. Is like the reason why we do this work is because we want to provide earth science information and regulation to make Oregon safe and prosperous. So the way what that looks like is we have folks at in agency leadership, and then DOGAMI is split into two main programs. On one hand, we have the Mineral Lands Program, which is fee-based and kind of does a lot of the regulation of surface mining and exploration for a number of, regulation for the state of Oregon. And then on the other hand, the other part of the program, and that's based in Albany. And then the other part of the program is the Geological Survey and Services, and that's the program that I am housed in. That includes all the work that colleagues like Bill Burns and Nancy Calhoun have been working on to do landslide inventory. And then looking at flood and channel migration mapping, doing earthquake and seismic hazards work. Then we also have the tsunami and coastal hazards group, and that's basically John Allen and Laura Gable, who are based in Newport. And then we also have the geological and mineral resource mapping, which I'll get to touch upon in just a minute. And underlying all of that is we have the LIDAR program, which is fundamental to the work that the agency does. And it's exciting to hear that Ian is going to be giving the talk at Kennedy School about this, about the LIDAR program in next month. So wanted to share some changes and just some updates of from the staffing perspective of folks who are doing work that is related to earthquake geology. So many of you might have already met our DOGAMI's executive director, who's also the state geologist, Rory Day Sturut, who started in 2022. You might also know Jason McClary, who had been Eastern Oregon geologist for a very long time and is now stepped into the Geological Survey and Services program manager. And he's based in Baker City at the DOGAMI office out there. Reed Burgett, he started a few months before I did. And Reed is a graduate from University of Oregon. Also has expertise in active tectonics and tectonic geomorphology and earthquake geology, but he's leading up the LIDAR program right now. Then I was hired in December of 22, and then Michael Darren, who is he's right now he's more closely tied to the state map program and the mineral resource mapping program, but a lot of the work that his background is also in structural geology and tectonics. And a lot of the mapping work that he is doing and collaborating with other folks in that team is going to inform a lot of the information and a lot of the information that we have about earthquake hazards and specifically fault mapping throughout the state. Also want to mention, I don't have photos for them, but Vanessa Swinton, who is a PSU graduate. She also started recently at DOGAMI and is working also in the state map program. Caleb Scarberry has also transitioned over from the Montana Bureau of Mines and Geology, and he's going to be working on economic geology questions in Eastern Oregon. And then we also, another recent hire was Richard Walker, who is who will also be also has expertise in structural geology and is going to be doing some pretty cool projects. So this is a little bit of kind of some of the changes. And I guess the other important piece that I didn't mention is we have Ian Maiden, who was senior scientist at the time of his retirement. He retired in June of 2022. But so that was a big change and a big transition that the agency has been going to. So before Ian retired, one of his last significant contributions was the publication of the first version of the Oregon Seismic Hazard Database. So this is a comprehensive database, has a great report that accompanies it. It has a lot of GIS information and kind of the most up-to-date Cascadia earthquake scenarios that were produced and kind of in collaboration with folks at the USGS and kind of updating a lot of the probability and earthquake hazards throughout the state, and it's a pretty major. There's a pretty major update, so kind of would encourage and recommend to check that out. We also want the other important piece from DOGAMI is that the state map project or state map program, which is part of the Geological Survey and Services program, is a partnership with the USGS to map 7.5-minute quadrangles throughout the state. So the way that usually works out, or the way that it works, is that state agencies propose mapping specific quadrangles to the USGS, and then if the grants are accepted, then the state needs to provide matching funds in order to complete this work. So a lot of the focus recent state map projects have been in northeastern Oregon, and specifically in the Wallula subbasin of the Umatilla Basin, right along the border with Washington. So doing a lot of updates and mapping in this area. 2023 published the Milton Freewater and Bolus Hills 7.5-minute quadrangle. Also 2023 we have the Athena 7.5-minute quadrangle and a couple of other recent ones that also are outside of the Umatilla Basin, but are other priority areas for DOGAMI to get mapping. And the key motivation to do a lot of this mapping is water resources and earthquake hazards. So that's those are kind of the main purposes that DOGAMI is proposing to go back and study these areas in greater detail. Other kind of ongoing projects and kind of other recent updates is we have like the landslide mapping program that I mentioned earlier with Bill and Nancy they've been very active, working currently with Anna Tsitsavas, who's also PSU a PSU master's student, as she's started an internship, doing a lot of really cool work, and kind of doing a lot of detection and mapping and multi-hazard risk assessments, and kind of working on the state landslide information layer, also known as SLIDO. There's a new version, version 4.5, which is going to be coming out in the spring. So keep an eye out for those upcoming announcements. Some pretty cool work that's been going on. Then in terms of tsunami and coastal hazards, we have a lot of, there's studies, like the entire coastline, it has been completely done in terms of impact analyses for what the impact of earthquake and tsunami would be on these communities, doing modeling using FEMA has a system to kind of help emergency planners and communities prepare for the coastal hazards. This figure that I have right here comes from one of the recent reports. This by Laura Gable, John Allen, and Fletch O'Brien, and this is looking at wave arrival time from the Cascadia subduction zone earthquakes for the tsunami, depending on where you are, timing of how long it would take those waves to arrive. Then one of the other big areas for the Geological Survey and Services program is we have a series of FEMA-funded projects under the Cooperative Technical Partners Program, which are basically multi-hazard loss estimations that are done on a county-by-county basis throughout the state. Just recently, we just had one published for Benton County in 2023, and then Alex just let me know that there's a one for Morrow County that is going to be published in the next few weeks. So these are also great resources for anybody who's within Oregon. If you go into the publication search, you can search for these reports and get a sense see if your community has already been studied, and it's another good resource to help prepare and help become familiar of potential impacts that are modeled using this HAZA system. And finally, want to highlight the LIDAR program, which as of 2024, or hopefully by the end of 2024, is going to have coverage for the entire state in LIDAR layers. The biggest gaps that existed are these pinkish areas that are highlighted out here. And these are areas that are in progress, and these are part of the USGS 3-depth LIDAR program. So this is going to fill in a lot of the gaps that existed for within the state. So right now, what Reed and Rob Hairston Porter are what they're busy working on is figuring out repeat LIDAR passes and starting to gather information. And it's really exciting to get to be a part of the agency as we're going, because even as a graduate student, I was always excited, and I'm just spending hours looking at the LIDAR that DOGAMI has provided. So it's pretty great that very soon we're going to have the entire state covered, and we'll be able to start doing repeat runs. All right, so I've got about 4 more minutes, so I'm going to try to go through and share a little bit more about Wallula Fault Zone, and also a little bit of what are ongoing state map projects. So I'm not going to spend a ton of time going over this map. This is showing the current or existing projects and recently completed projects as part of that state map program, where we're mapping those 7.5-minute quadrangles. And we have the up here is that the Wallula subbasin of the Umatilla Basin, which I highlighted, and this is where we're going to be taking a look at soon. One of the other priority areas is the Harney Basin. So you can see there's a number of quadrangles in there within the Harney Basin, and there's some other ongoing work that we're going to be pursuing in the near future. So a little bit about the Wallula Fault Zone, since in the last couple of minutes that I have for presentation, for talking. And we also want to, I know that I'm not leaving a lot of time for questions right now, but once the recording stops, happy to answer additional questions as we move forward. So the Wallula Fault Zone is located and is part of what is known as, what some people refer to as the Olympic Wallula lineament, which has been recognized for for a very long time, is looking at the structural grain, looking at structures that basically connected in the Northwest, Western Washington to Southeastern Washington, Northeastern Oregon, a series of lineaments and existing structures all along here. And it is thought that there's some interesting, there's proposals about the tectonic nature of the Olympic Wallula lineament, or OWL for short. And where we're going to be looking at is the Walla Walla Basin, which is right in here and is kind of near the termination, or close to the termination, of the Olympic Wallula lineament, and the Wallawas are going to be right here. This is an area of really interesting geology, but has also, and the Walla Walla Basin has produced some of the more damaging the most damaging earthquake in Eastern Oregon and Eastern Washington, and that was the 1936. It's called the State Line earthquake. There's some pretty cool work going back. There's Benji Brown from late 30s. Like 39, I think. There was a publication in the Bureau of BSSA that was published on that, but it's an area that has been interesting for quite a while. And in 2018, we have relocated the epicenter of that 1936 earthquake, and that's it's within that Walla Walla Basin and is right within the mapping area that I'm working on. So I know we're coming in on 12. So
we are at our hour,
it?
But I'm not going to ask you to stop.
Okay.
I mean, please go over 5 minutes or whatever. I don't want you to rush through the last piece of it. And some people came for the Wallula Fault Zone. Cool. So if you could start the sentence you just said, so that I can edit out what I'm saying here, and then just continue.
Sounds great. Thanks, Paul. And we're making good progress. So as I was mentioning, recently, it was 2018, Brochure and Sherrod relocated the epicenter for the earthquake because the instrumentation back in 1936, there wasn't instrumentation that was very close to the epicenter, so there was some errors. There have been questions about how it was located, and this recent study kind of identified the epicenter as being very close to the community of Umapine, which is just south of that, just south of the state line between Washington and Oregon. So that's the star is going to be that suggested epicenter. All right, so a little bit of the kind of where I'm at right now. So I've been doing a lot of background research and been doing a lot of digital elevation model analysis and analyzing the LiDAR data and doing some of the geologic mapping. So the general sense, as we zoom into the Wallula, into the Waterman Quadrangle, which is where I'm working, this right here would be considered like the main strand of the Wallula Fault Zone, and generally has like a strike slip sense of motion, but it's also oblique, so it's mostly going to be right lateral dominated, but it does have a significant vertical component to that displacement. And then the other piece too, right off of the map, on this right-hand side, we have the height fault system, which trends roughly northeast to southeast. But this is you have this intersection of these two principal domains where we have some dip slip dominated displacement that's happening to the east of the quadrangle where I'm mapping, but within within the quadrangle that I'm mapping, it's looking like you have a combination of both that strike slip and the normal sense of motion to kind of have some really interesting oblique structures that are developing within the mapping area for the Waterman quadrangle. And this is back in 1993. Mann and Meyer, they were working on the Olympic Wallula lineament question, and they also did some trenching on, I guess this fault is referred to as the Horse Heavens Hills fault by folks in by some, and they did some trenching out here. And I should also add that colleagues from the USGS, including Lydia Stage and Steve Angster, are working on the Washington side of the Wallula fault zone. So they kind of just working on the eastern extent. So we're kind of working on the Oregon side, doing some mapping and looking at the faults, and they're doing some work out there. And this right here is just an image of what the landscape looks like out there. It's beautiful. It's wide open, big sky. It's beautiful getting to do the work. This is going to be mostly Columbia flood basalts that make up these highlands down here in the south, and then it's going to transition into the Walla Walla Basin, where you have some bedrock outcrops that are mostly that are exposed mostly through structural deformation, and then we have Missoula flood deposits that filled in the Walla Walla Basin and created many of the deposits that we see to the north. Here is, so yeah, we have that. And then where I've been spending most of my time has been kind of up on top of the high ground, on top of the Columbia flood basalts, which are overlain by loess deposits. And this is just kind of an example of potential unmapped fault, new fault that hadn't previously been mapped. Lucky enough to find a little quarry that's right there, and looks like we have some potential reverse fault or thrust fault that is up with the head wall being here on the right, and then we have on the left the downgoing block. So we'd have that potential motion. So there's some pretty interesting structures, not only up here where we have the main Wallula fault zone, but down here as well. So and that's where Jason and I have been interested. So that would turn into a video. So Jason McClary and Carrie Azzopardi currently have a new geologic map that's in review for the Adams quadrangle. And this is the quadrangle that's directly to the south of the Waterman quadrangle where I'm working. And Jason and Carrie have identified some northwest southeast trending valleys that appear to be fault controlled. And the geomorphology in the loess in here is really interesting. So we have a lot of triangular facets that occur along the steep face of these asymmetrical valleys that have developed within the loess. Now, there's a suggestion of active faulting, and I'm not going to. There's the facets, and there's other evidence for them, including tephras that have been identified within the loess that are helping us figure out the geochronology. We're going to be sharing more results about this at the GSA meeting in Spokane to talk a little bit more about these particular structures and the various styles of faulting that have been identified, including kind of these linear, oblique, oblique normal faults, including, but then also have evidence of some strike slip faults that are preserved within the landscape. So there's some pretty cool areas to go and take a look at some of the faults out here. And I'll also so that kind of, I'll leave Wallula there for now. We can come back to it if there's more questions. a couple of other projects that I have going on. Going to be publishing a Cascadia loss estimation for the Springfield Eugene area. That's kind of in progress. I'm excited because this will include a Spanish presentation, and we're putting together information sheets that will be bilingual as well. Other relevant initiatives, we have the Shake Alert, which hopefully everybody has access to on mobile devices. If you're within Oregon, that early earthquake warning, always want to highlight that. And then we're also involved in the Cascadia Region Earthquake Science Center, which had its kickoff meeting back in October and has some upcoming stakeholder meetings in June in the Portland area. Then kind of projects down the line, we'll have going to be working on updating the Quaternary Fault database for the state of Oregon, also developing a multi-hazard clearinghouse plan to help coordinate scientific reconnaissance to major events, such as the Cascadia earthquake. We're also pursuing funding to do a kind of a regional impact analysis for a Cascadia earthquake, which will compile and update a lot of the multi-hazard risk assessments that that DOGAMI has been publishing into a statewide so that it's available for the entire state as opposed to individual counties. And also interested in pursuing looking at paleoseismic studies in Eastern Oregon. So exploring options with colleagues and collaborators with in the USGS and the Bureau of Reclamation for some of this work to help better understand the earthquake hazard. So thank you so much. I know I went over, but I'll be happy to answer any additional questions or any questions at this point. So thanks.
That was wonderful, Lalo. Thank you so much. And it was fun to hear your background, because I think that gives more depth to where you're going with your studies and work with DOGAMI.
Yeah.
Starting back at your start of your talk, when you got into the tsunamis in the coastal area, there was a question about 5 to 15 minute tsunami wave arrival time is extremely short. Please describe the earthquake sensor system and how alerts are communicated to the general public. I know that's a really big question, having lived near the coast.
Yeah, no, that's a really great question. So so I'd say in terms of the alert, in terms of the Shake Alert system, I think maybe that would be one place to start. So the Shake Alert system is basically set up so that there's sensors that are, the network is run by the Pacific Northwest Seismic Network, and they have it's a pretty rapid detection system and communication system that basically detects the early, the initiation of the earthquake event, and then sends out that alert through the Pacific Northwest Seismic System, through the Shake Alert system, which then will hopefully, the farther away you are from the earthquake origin, the more warning you're going to have. The idea is hopefully for residents to get at least 30 seconds of early warning, which can initially help you take those first protective measures like dropping, covering, and holding on. If you're on the coast, you'll experience the shaking. It will be very violent shaking, and I think that the main point to highlight from this figure is, given the time for the earthquake to arrive, it's one of the common responses when humans experience an earthquake is like the milling effect. So sometimes 5-10 minutes of kind of walking, taking stock, ambling around. I think the key point here is that as soon as the shaking stops, we need to follow evacuation routes. And I didn't include a link on here, but I also wanted to highlight the Nanus system, which is one of the resources. It's the Ocean Observation Center for the Northwest. And they have apps on the website. I think it's the website has a main capability that you can plan your escape routes, or if you're going to the coast, you can figure out where the safest evacuation route is going to be. So basically, when you feel shaking, once the shaking stopped, stand up and head to higher ground as soon as you can when you head to the coast.
Okay. In other words, keep your ears open.
Yes.
Be aware. So
Yeah.
the next questions actually jumped to Alex, bless his heart. Thank you very much, Alex. Answered a question about the number of geologists with DOGAMI. But the next questions jump to, is the Wallula fault zone related to the clockwise rotation of Oregon?
So that's part of the question. So that's part of what we're exploring. Is thought that, I mean, all of these general structural features that we see within the Olympic Wallowa lineament, it's thought that it is related to that rotation. So, and I didn't plot the GPS station data on here, but here we have, if we were to look at it, we'd see the GPS vectors moving here to the north, and then here they'd be moving kind of westward or eastward relative to North America. And then kind of you'd see a little bit some rotation with minor components out here in northeastern Oregon, southeastern Washington. So it's thought that like some of the structures that are developing are a product of that rotation and that impingement of the Oregon block into Washington. So, and while we're talking about tectonics, just going to throw it out there because there was a question about the Portland Basin being a graben, and the short answer is that the Portland Basin is part of the Forearc Basin, or the Forearc Basin, which is also known as the Puget Lowlands Puget-Willamette Valley Lowlands Forearc Basin. It has, and the terms can it can be a big mouthful, but we have that Forearc Basin that extends from Eugene in the south all the way to western Washington, and all of that depression forms because of this active Cascadia subduction zone. And then the Portland Hills are a product of some of that strike slip motion and kind of most likely related to that rotation of the Oregon block. So.
All right, thank you. And I think you pretty much answered John Ogden's question about what's your opinion of the Olympic Wallowa lineament, and is it a thing, and is it a collection of unrelated features? And it sounds like that's what you guys are exploring.
Yeah, it's one of those questions, and I'm not confident enough and don't have enough information yet to be able to give a definitive opinion yet.
So I have a question about you alluded right at the end to paleoseismic studies in Eastern Oregon.
Mm-hmm.
Now, I only had the advantage of having LiDAR at the tail end of my career. Mm-hmm. I had done all of my work using air photo interpret and a stereoscope here in Central Oregon. And one of the things that was confirmed with the LiDAR at the tail end for the Ochiko Mountains is that there's a lot of the scab stringer, that's in quotes, that we would see, which basically boiled down to faults that caught the Mazama ash and some of the other ash falls and became these wonderful growing zones for trees, do show up as definite evidence of movement across the top of the Ochiko Mountains. So that's one of those areas that I've always had a puzzle about, and I'm hoping that you guys might might be thinking about this. I know I've expressed it to both Clark Neuendorf and to Jason over the years. And I think it's one of those interesting puzzles in the center of Oregon.
Yeah, that's and I agree. It'd be really interesting to take a look at it, and it's I guess the yeah, it is an area that we are considering and are looking at, and I'd say kind of a lot of the motivation in central and eastern Oregon is to do to get a better understanding of how the faults are behaving out there, specifically where there's critical infrastructure that crosses the area. Because usually seismic hazard is usually thought to, or is usually considered to be the exposure of humans and people to those earthquake events. But I think there's enough there's enough faults that cross some major transportation corridors and lifeline corridors that kind of merit a lot of that work. And I know there's a couple of reservoirs. There's a reservoir in the Ochoco. And we're interested in looking at what are some of the faults that are working on. And I know, say, Ray Wells from University of Oregon is also doing a little bit of work in Central Oregon, kind of south of the Ochocos. So it is an area that we are actively interested in and looking forward to go back.
Good to hear that.
Mm-hmm.
Any other questions? Alyssa, Angela?
I think there's one that we could pull in, and someone had asked about the connection of this like fault zone to the rotation of the Oregon block. And my thought along that line is kind of, how does this fit into that sort of a picture?
Yeah. So So kind of if we're thinking about I guess let me go back maybe to the Wallula, the one that shows. So one of the potential ways in which this might be fitting into the rotation is that we're having there's as Oregon is moving northwards and impinging on Western Washington, and we have the rotation of the Oregon and Washington block that are happening. We're going to be developing a variety of structures, including kind of like the Rattlesnake Mountains, and there's the Folden Thrust Belt, Yakima Folden Thrust Belt. That is going to be out here, is going to be produced by that impingement. And then as you have the rotation, you're going to create the blocks. You're going to have to, there's going to have to be some accommodation space. And as the block is rotating, that accommodation space is causing strain to accumulate and kind of start moving the faults a little bit more on Eastern Oregon. So it's I think that might be one way in which they're connected. But again, I'm still figuring out like how these faults, or how the Wallula fault zone is going to be responding, because the other piece too is like, once you're getting in this part of Oregon and you start crossing into basin and range, you end up having that transition zone. So I think that's ultimately going to be the key point, is that the transition zone between some of the effects of rotation, and the basin and range extension that is going to be occurring to the east of here, or kind of around here, is going to be you're gonna see some of that transition zone like within the Walla Walla Basin itself.
And there was one question, thank you, Lalo. There was one question too, I think Patty asked it, is, are there any physical features where somebody could go find the height fault? Is it near, what town is it next to?
Yeah, so you can, if you track down that Milton Freewater publication in the DOGAMI publication page, can load the map on an iPad, and if you want to go spend a great time in exploring the area around Milton Freewater, there's some really great exposures and some really interesting structures to go that are highlighted within that map. And just a geologic excursion within the Walla Walla subbasin, I would highly recommend it. You get to see some of those really great Missoula flood deposits. There's a world-class Tushy bed deposits that I would also recommend to go check out. And so there's some of so that you get to see some cool faults, and you'll also get to see some cool Missoula flood deposits, and also some great Columbia flood basalts. And I guess I've heard the vineyards around here make wonderful wine. I haven't tried it myself yet.
And that would be true. And Scott Burns has got some really interesting talks related to our volcanics and the soils they generate. So Paul, Paul and Gary, I think we are still recording, and I will hand it off to you. And Lalo, thank you so much for an absolutely wonderful talk. And Angela, thank you for that history of eruptions in Iceland. Cool.
All right.
And thank you for everyone who stayed a little late this time. We had such excellent speakers. Wanted to give you a little more time, and also just loving the way that Alyssa and Carrie are managing the questions and handling the conversation. There's a moment I'm always listening because I edit the videos later. I'm always listening for sort of pull out quotes that I can use for a cold open at the beginning of the intro. There's a moment when Carrie brings up the Ojiko faults, and Lalo says, "Yeah, there's a tone of wonder and enthusiasm as one professional talking to another. That is exactly what people want to hear. You know, when those of us who are amateurs get to listen in on the conversations between scientists, that's the, you know, it's those frontiers. It's that excitement. It's that curiosity, and hearing, as Lalo was able to give us the great detail of everything that DOGAMI is doing. Now, you may remember, some of us, GSOC is a non-political organization. We've got Republicans and Democrats in the room, and you know, we stay pretty non-political. But a few years ago, we got political because DOGAMI was on the chopping block, or the governor's chopping block, and we got involved. And I'm proud of that effort. I think we were part of the effort among that in the geological community, professional community, and even industry, to save the organization. And this is why, because DOGAMI does so much important work for the state of Oregon. And we have a long history going back about 70 years of folks who at GSOC who were also working at DOGAMI, and vice versa, DOGAMI state geologists who were presidents of GSOC and so forth.